Hello, everyone. Welcome back. In this recording, we are going to talk about Lecture 4, the combined law of thermodynamics. In Lecture 1, 2, and 3, we discussed the first, second, and the third laws of thermodynamics. In this lecture, Lecture 4, we're going to talk about combined law of thermodynamics. I have very short historical sketch about combined law. The first law and the second law were discovered, but they were separated. One of the main reasons was that the first law was about equal. The energy conservation, the internal energy increase equals to the energies for the surroundings put into the system. However, the second law is about the entropy production. The entropy production must be positive due to the internal process or processes. So you see the equal and the unequal, they could not put together. And here Gibbs visited Europe from the winter of 1866 to June 1869. And I call this transfer learning of knowledge. And Gibbs was educated in the United States. He had knowledge of science. Then he went to Europe, in France and Germany, and he learned new knowledge. He transferred his brain, so to speak. Like today, we're talking about the machine learning, large language model. So he realized these two laws, first and second laws. Then he also realized that if he considered equilibrium system only, then the unequal sign for the second law becomes equal because there's no entropy production in an equilibrium system. So he published a few papers in early 1870s. In 1878, he published a combined law. But even before that, in 1873, he showed the internal energy should be a function of entropy and volume. So that's how typically thermodynamics is taught today, or in most textbooks. That's why thermodynamics is thought to be for equilibrium system only. However, we could actually put the entropy reduction into the system. And of course, there's a lot of work in the literature, but I think Max Hillert, he was systematically put the entropy reduction into the combined law for non-equilibrium systems. As shown that his book, this is second edition in 2007, but the first edition was in 1998. Look at the title of his book. It's phase equilibrium and phase diagrams and the phase transformations. So this is really the equilibrium and non-equilibrium altogether combined. So I really think Max Hillert was the person systematically put the two together in this wonderful book he had. However, in both Gibbs's publications and Hillert's publications, the chemical potential of individual components was directly added into the combined law. So it was not clear how the chemical potential was introduced. They just say, okay, you add a component I, then you have a chemical potential of that component I. So when I was just looking at this one a while ago, I was always wondering how this chemical potential of a component should be defined. So in Max Hillert's book, so he wrote the combined law with du plus equal to dq plus dw. he had HMDN. So I followed his equations in this book we had published in 2016. But however, as you have seen in this lecture 1, I wrote the first law differently. I wrote the du equal to dq plus dw plus summation of ui dni. Instead of h, which is typically for enthalpy, as we will discuss later, I put the internal energy, the total energy of a substance. That means each substance, each component has an internal energy. Of course, this ui, as we showed before, is partial internal energy, because when the components are put together, they affect each other. So it was until 2020 when I was writing an overview paper of ActMed, I realized that there's inconsistency here. So in this paper, I explicitly defined the chemical potential of a component as follows: equal to ui minus TSI. So we're going to talk about the SI. We talked about ui before, but in this lecture, I'm going to talk about SI, which is a partial entropy of a component I. So that means this book needs to be updated. So I'm going to work on the second edition of our book. And the major change in the book is that we're going to correct HI, which is corresponding to what Max Hillerty used, by UI in the 1, 2, 3, 4 equations. And I also want to point out one error. The phase regions of alpha and epsilon in the figure 3.2 for POIM was switched. I want to thank Professor Wen Hao Song to point that out. So when Gibbs derived this combined law, he was talking about a closed system. So the mass was not changing. So internal energy, he derived internal energy is a function of entropy and volume. So Maxwell in UK got very excited. And he made the model by his hand, actually just a couple of years before he passed away. This model is the picture from Wikipedia. This model is at Yale University. And also Wen Hao Song had a very nice 3-dimensional digitized the model. So in 2022, when I had my sabbatical leave at the University of Cambridge. So I was giving a talk at the Cavendish lab about our work on thermodynamics. I mentioned about this model. There's one person in the audience who pointed out, no, there's another one at the Cavendish lab. So the next day, I went there and I found it. So this one is, so this is the model, physical model, still in Cavendish lab at the University of Cambridge. It's amazing. And this is a drawing Maxwell had on this 3-dimensional surface of this model. As you can see, the lines are drawing on this model. It's amazing. Think about it, it's 1874. That's 150 years ago. And this very nice energy surface. I call it energy landscape. Of course, that's the internal energy. You have the apex, as mentioned at the earlier of my lecture. You have another apex. You have the valley here. Then you have the saddle point, if you can go as the other side, for example, right? So you may have more than one minimum on the other side of the space. But here, this one, of course, you only have one minimum, which goes down all the way here. So you have a valley, you have basins, you have the apexes, and you have the saddle point. This is for total energy. But of course, if you go to finite temperature, you will need to have a free energy. That's really the focus of our research, is to get the free energy. a fancy landscape of a system as all the internal variables, entropy, volume, all the compositions, or you can have the stress, electric field, and so forth. Okay, so we have to get the in this process to combine this first law and second law. So we have to think about entropy, right? Because the entropy production. So that means we have to first work out what the total entropy change of a system with these three exchanges between the system and its surroundings. So it's heat. We know that already a heat change divided by T is equal to ds. So that's the entropy change of the system due to the heat exchange. And then we have the component. Remember that in the third law, in the lecture 3, we talk about the third law. Each component has its own entropy, right? Because, for example, the pure component I, you can do the heat capacity measurement and do integration from 0K to whatever temperature. You get the entropy of that component, pure component. Of course, when the components are together in a solution, you cannot measure them individually, but you can calculate them, as we will show later. And we always learn in the textbook of thermodynamics that the work does not affect entropy. However, the surrounding puts work to the system, it affects the internal processes, right? So the system will do something and rearrange it. Of course, you put heat into it, the system is also going to rearrange it. I have some internal process. You put some component into it, systems are also going to have some internal processes. So the work it contributes to that to the occurring of internal processes. That means we have three contributions to the total entropy change of the system. Okay, it's in the system, right? So we have the heat. The heat is add heat or remove heat. You have the mass. You can add the mass, a component, or remove the component. Then you have the internal processes. That's entropy production due to the internal processes. Second law. This term has to be positive for any internal processes. Okay, so let's look at the SI, the component, I call it partial entropy of a component. So let's go back to this equation. This equation has a very important information which is sometimes overlooked. You see that entropy change of a system is heat, it's also a mass, right? If you change the mass, entropy change too. That means it cannot change mass independently without changing entropy. So ds depends on dni. They are not independent. This is very, very important, which has been overlooked in the literature. So look at this equation. If the system is an adiabatic system, that means no heat exchange. And if it's at equilibrium, there'll be no internal processes. So if we add dni only, component I only, then we get entropy to the dni derivative given by SI. Right? We know that whenever you take a derivative, we call it partial. Okay, so partial entropy of component I for a partially open system because other components are not exchanging between the system and the surroundings. So now we introduce we have the partial energy, partial internal energy. Now we have partial entropy. And turned out these two partial quantities are so important in defining the chemical potential of component I, which has not, as I mentioned, which was not determined or defined in Gibbs or in the Hiller's equations because they just add. So you add a component, you have a chemical potential. But as you will see later, it actually we can define it uses two partial quantities. Okay, so we talk about internal process, right? So internal process, it takes place because it's something driving it. Okay? So there's driving force for that internal process. So to produce entropy. So we have to define what that internal variable is changing, right? Because the internal process is it means something's changing. So it could be many things. So we just call it mass unit, call it the internal variable. So that means we have the internal variable to represent that internal process. So the internal process is psi, and the d psi is the change of that internal variable. So that internal variable, as I just mentioned, is the driving force for the internal process. We call it D. Again, we follow what the mass unit used. And this internal process will produce entropy. Okay, so T times entropy is the energy. So driving force times the process change gives the energy change. So if we move D to the other side, we define the driving force equal to temperature times the entropy production derivative to the internal variables, to the process change. Of course, in a system, there could be many independent internal processes, right? Or it's never be only one process. As actually we'll talk about later in this lecture series, we call it cross phenomenon. Because once potential changes, one variable changes, all other variables will change at the same time. So you have this kind of cross phenomenon. Okay, so how can we make combined law then? So we have the equation. We have the equation from before. The ds has three terms: dq over t, si dni summation, and the dips. Now we can move t on the other side, and times t on both sides, and then move these two terms to the other side, we get dq. Okay, that's what we have. Now I have two minus signs here. And then we have the combined first law. We have the dq plus dw plus the summation of ui dni. So we can substitute the dq by this equation. So we got the combined law now, right? Because the second law is embedded in the d psi here for entropy production. Now we put them together, we find we have ui minus tsi in front of dni. That means when we put entropy times temperature here, we have to remove that entropy by that element because dq doesn't have that element contribution. So now we have ui minus tsi in front of dni. That quantity is the chemical potential. The ui, mu I equal to ui minus tsi. So it's the first time defined in the paper I mentioned in 2020. Which it's where is it? It's somewhere earlier here. It's right here. This paper, active math. That's the first time when I was writing that paper, I realized this problem, this inconsistency. So we get the combined law. It says combined law actually is the same form as in Hilleter's book. The only difference is that how the mu I was introduced, how it's defined. By starting with the ui here, then we can define the mu I from this combined law. It's also very important to realize that the internal processes does not change internal energy. Internal energy is completely determined by the three exchanges between the system and its surroundings, that's heat, work, and mass. However, the internal process change entropy. Okay. That's why the entropy is so important quantity for us to define how system evolves. Okay, so let's give a summary of the combined law. So we have the surroundings, we have this a system, and the system and its surroundings. So we talk about exchange. We call external. The system exchanges with its surrounding, the external of the system. There are three types of exchanges: like heat, work, and mass. And from the energy conservation, we got the first law. The internal energy change must be equal to the three energies the system receives from its surroundings. But when the system receives energies from the surroundings, it's going to do some work or to have some internal processes. We use xi to represent it. The internal process must have a driving force with d to represent it. And the second law says that the d times dxi must be positive. That means the problem is moving forward, dxi is positive. Then you have driving force to move that process, internal process, side together is positive. It's represented by the entropy production, DIPS, on the left side of this equation. And by using this definition of dxi, then we can calculate, we can write an equal equation for dq. dq now is a function of TdS and minus the TSI dni, which is the entropy change due to the mass and the internal entropy reduction. And then we get a combined law. The same combined law by Gibbs and also by Hillard. In the Gibbs, as we will discuss in the future lectures, that the Gibbs talk about an equilibrium system with this one equal to 0, but Hillard kept this term here. That's why in my paper I used the Gibbs equilibrium thermodynamics and Hillard non-equilibrium thermodynamics. The next lecture is lecture 5. We talk about the internal processes, dxi. Thank you.